This is the arithmetic logic unit that I've pulled out of my 8-bit homebrew processor. It's pretty cool. I can already do addition and subtraction on 8-bit numbers, and by using the carry flag register, actually on arbitrarily sized numbers. It's missing a pretty important feature though. Many interesting algorithms require shifting bits in a number to the left or to the right. If this ALU had this ability, we could implement things like multiplication, bit reversing numbers, checking if individual bits are set. We could do some form of compression, parity checking, and a whole bunch more. So this would be an important feature. Today, I want to give this ALU the ability to shift bits in a number to the left or the right. We're only going to do the simple version for starters. We're going to shift the bits one step to the left or one step to the right. A general shift by an arbitrary amount requires a barrel shifter with quite a few multiplexers. I think I'll do this as a separate unit down the road that we can hook into the CPU. But let's get started with the simple thing first. The way I plan to implement this is to actually take the left-hand side input of the ALU as it comes from the CPU and shift the bits in that number to the left or the right, and then feed it into the adder and to the output of the ALU. And if we then feed a 0 into the right-hand side, the adder will effectively be disabled and the ALU will just do the shifting. If you're familiar with James Sharman's fantastic 8-bit CPU series, this will look fairly familiar because he has a very elegant ALU design, and a lot of this ALU is inspired by what he did. Check out the link in the description if you haven't seen that series yet. It's really worth watching. To get started, let's quickly figure out the architecture and how we're going to do these shifts. And let's think about what the concrete instructions are that we want to support. Right now, the ALU just consists of an adder, which takes a left and right-hand side input and the carry input. And we have the option to invert the right-hand side input to perform subtraction. However, to do bit shifting, we don't need both of those inputs. We just need one number. That's the number we want to shift left or shift right. And then we want to store that back into the register file. We're already modifying the right-hand side input to the adder to implement subtraction. So I think it would make sense to modify the left-hand side input of the adder to be able to do bit shifting of the left-hand side input. And then if we want to do a bit shifting operation, we can just set the right-hand side input of the adder to 0, such that the left-hand side, where we do the shifting, gets passed through the adder unchanged. So what kind of operations would we want to do? So from the register file, we're getting an 8-bit number with bits 7 all the way down to 0. One of the operations we might want to do is to shift these bits one step to the right. And now we need to decide what we're going to do with bit 0 that popped out of the number and what we're going to fill in at this topmost bit position, which is now empty. I think we'll have the most flexibility if we take the carry input that we're currently feeding into the adder and we fill this into bit position 7, the position that is now empty after the shift. And this carry input, if you recall, this is actually coming from a carry operation multiplexer. And with that multiplexer, we can select this carry to be the constant 0, the constant 1, or the current carry flag bit, which is going to be super useful. And similarly, bit 0, the one that we shifted out of the number by doing the right shift, we can actually take this and present this as the carry output of the ALU. This could be used to bit shift very large numbers or to implement the kind of population count where you shift individual bits out of a number and tally them up through the carry flag. Now, one thing we need to consider when we're doing this right shift and we're presenting bit 0 as kind of the carry output of the ALU, we no longer want to feed this carry output, this bit 0, into the adder as the adder's carry input. We want the adder to be mostly deactivated. Its right-hand side should be 0, and its carry input should also be 0 when we're doing shifts, such that it's not modifying the number we're presenting on the left-hand side. So quite importantly, now that we're doing these shifts, we need to separate the concerns of the carry input and carry output of the ALU itself, the entire unit, which is what we are reading and writing from into the carry flag register, and the carry input and output of just the adder circuit that's in there. For some of the operations, like addition and subtraction, we want to have the adder's carry input and output be just the carry input and output of the entire ALU. But for some operations like this shifting that we're trying to implement here, we want to have the adder's carry input and carry output mostly disconnected, not factor into the operation. So when we're doing this right shift, we explicitly want to set the adder's carry input to a 0, such that it doesn't affect the result. And we're just going to ignore the adder's carry output in this case, because it's always going to be 0. And if we're shifting bits to the right, it's quite natural that we'll also want to shift bits to the left. So if again we get the number from the register file, bit 7 down to 0, we can take these bits and shift them one position to the left. This vacates the lowest bit position, position 0, is now empty, and it makes the upper bit, bit 7, pop out of the number on the left. And again, the same reasoning as with the right shift, this now empty position at bit 0 here, we're going to fill in with the carry input, which is produced by the carry op multiplexer. This allows us to shift in zeros, ones, the carry flag, or whatever else we connect to that multiplexer. And bit 7 that pops out of the number at the top will feed into the carry flag register, will present as the carry output of the ALU. And this allows us to take a register, shift the bits to the left, whatever we shift out gets stored in the carry flag, and we can decide with the carry op multiplexer what we're shifting in at the bottom. And just as before, in this case, we want the adder's carry input to be set to 0, such that the adder doesn't add anything to the shifted result. So this is how we would modify the left-hand side input to the adder to implement the right and the left shift. But if we don't want to do a shift operation, if we want to do a regular add or subtract or any other operation, we also want the ability to just take whatever the bits are that come from the register file and pass them through unchanged. So when we get bits 7 down to 0 from the register file, we want to be able to just leave them as they are and pass them on to the adder. Let's call this operation RD for the destination register, because we've generally called the left-hand side input of the adder RD and the right-hand side input RS. And in this case, because we're not doing any shift operation, we want to set the carry output of the ALU to whatever the carry output of the adder is. And similarly, the adder's carry input, we just want to set whatever the carry input of the ALU is. This is basically how the ALU works at this moment. The adder's left-hand side input is directly connected to the register file. The adder's carry input is directly connected to this carry input multiplexer, so we can pick what carry we feed into the adder, and whatever carry output the adder produces immediately gets forwarded to the carry flag register as the carry output of the ALU, which should be stored in the carry flag register. So now we have 3 different shift operations that we want to do on the left-hand side input. Now it's worth considering that to make this work, we need the right-hand side input of the ALU to be 0. And likewise, when we extend the ALU, there will be cases where we want to have the left-hand side input of the ALU to be a 0, such that the right-hand side gets passed through unchanged. We're probably going to implement some logic operations on the right-hand side input, and if we use that functionality, the left-hand side should just be 0, such that the adder just passes through the right-hand side unchanged. So let's add a 4th mode here, because multiplexers generally come in powers of 2, and let's just call this the 0 mode. And instead of passing on whatever comes in through the register file, we're just going to feed a 0 into the adder. And since we're not doing any shifting, we'll just feed the adder's carry input and carry output through to the ALU's carry input and the carry output. And so these are the 4 shift operations we want to be able to do on the left-hand side input of the adder. We want to be able to shift right and shift left, pass on the RD bits from the register file unchanged, and feed a 0 into the adder. And we can implement this pretty easily with a whole bunch of 4-way multiplexers that have 4 inputs and 2 select signals. So let's call the select line of these multiplexers, the one which selects which row here we're implementing. Let's call that the shift operation, and let's just assign a few numbers. Intuitively, it would make sense if the 0 operation would be shift operation 0, and then let's just count up. The RD operation, passing on the register bits unchanged, is going to be shift operation 1, shift left is going to be shift operation 2, and shift right is going to be shift operation 3. And this should be pretty straightforward to build up on a breadboard. We can essentially take each column in this table and turn it into a corresponding 4-way multiplexer on the breadboard. So to implement this first column of the shifted left-hand side adder input, this consists basically of the left-hand side input into the ALU, which is the B7 down to B0 bits in the table here. And it also consists of the carry input, which is provided by this carry operation multiplexer that we've added in the previous episode. And that multiplexer has its inputs 0 and 1 connected to the constant value 0 and 1. And inputs 2 and 3 are connected to the current value that is stored in the carry flag register. And then we can use a four-way multiplexer to pick which one of the rows in this table we want to use. We're basically going to use the shift operation as the select signal, and then operation 0, 1, 2, or 3 pick the corresponding row of the table. And then whatever this multiplexer selects, we are going to feed into the adder as its left-hand side input. On the right-hand side, we already have this XOR gate that we can use to conditionally invert the right-hand side to implement subtraction. This is currently connected to bit 0 of the carry operation, which is also a 2-bit signal. This we've implemented in the previous episode. And this potentially inverted right-hand side will be feeding into the adder as the right-hand side of the adder. Then we also need to pick what the carry input of the adder is going to be. And we have a dedicated column for that where we specified for each row in this table for each shift mode what the corresponding carry input to the adder should be. This is basically taking either a 0 if we're doing a shift or the carry input signal and forwards this to the adder. And again, we're going to use a four-way multiplexer and the shift operation signal to pick which row in this table we're going to use as the carry input to the adder. And then for each of the shift modes, we've also specified what the overall carry output of the ALU should be. For the shift right and shift left modes, we decided that it's one of the shifted out bits. And for the other modes, we've decided to just pass along whatever the carry output of the adder is. So again, we can move this table down and use a four-way multiplexer with the shift operation signal again to pick which one of the rows in this table we're going to use. And this is going to produce the carry output of the overall ALU, which is what's going to be stored in the carry flag register for the next cycle. And then finally, we also have the result of the adder, which is just going to be the overall result of the ALU. So let's go build this up on the breadboard. Okay, let's get going. Let's build this up. I think a good location for the shift multiplexers is actually this spot here where the right-hand side XOR inversion unit currently is. Because I plan to eventually replace this XOR unit with a more fully fledged logic unit that will actually use up 2 breadboards. I'm planning to put it all the way at the bottom here. So it'd be good if in this spot here we would have the shift multiplexers that deal with the left-hand side. So let me sever these connections here such that we can move this breadboard down the slot and insert a fresh new breadboard here where we're going to put all the multiplexers for the shifting. Alright, great. So that's a fresh new breadboard for the shifting unit, and the right-hand side XOR unit has moved down here. To get started, let me connect the power rails back up, and then let's bridge the data lines that have to go from the right-hand side XOR unit to the right-hand side input of the adder here. Alright, that's the power connected up, and also the inverted right-hand side input hooked up to the right-hand side input of the adder. Now let me add the multiplexer chips. It's going to be 4-way multiplexer because we want to shift left, shift right, not shift at all, or inject a 0 on the left-hand side such that we can do more fancy things on the right-hand side in the future. And we've already used a 4-way multiplexer up here, a 74HC153 chip. These chips contain 2 4-way multiplexers, so we're going to use 5 multiplexer chips in total, 4 for the 8 bits to be shifted, and another multiplexer to deal with the carry input and how to inject carries into the adder. Let me hook up power and ground of all these chips. Next up, these multiplexers actually have an output enable input, one for each side, and if that is disabled, the output will just read as a 0. And it's an active low input, so we'll need to tie that to ground such that the output of the multiplexer is always enabled. Next up, there are the A and B selection inputs, which basically together form a 2-bit number which picks which of the 4 inputs is going to be fed through the multiplexer to the output. And since we want to have each bit of the number behave the same, we're just going to connect all the B inputs and all the A inputs of these multiplexers together. Okay, so that's the A input on pin 14 connected up and the B input on pin 2 all connected up. Up here for the carry operation multiplexer, we added these two green LEDs that show which carry operation is selected. And I think we want to do the same thing here. We want to have two green LEDs here that show the shift operation that is selected. Alright, so bit 0 is on the right hand side, bit 1 on the left hand side, same as up here. And we'll call this the shift operation of the ALU because it picks what we do in terms of shifting with the left hand side. The right hand side LED, the shift operation bit 0, we're going to connect to pin A of the multiplexers on pin 14 here. And the left LED, shift operation bit 1, we're going to connect to pin B of the multiplexers, which is pin 2. And so by connecting these two bits up to the instruction or somewhere else, we can pick what operation we do on the left-hand side path of the ALU. And now on each side of these multiplexers, we have 4 inputs corresponding to each of the 4 options we can select at the input. And all that's left to do is essentially hook them up in the right pattern. The easiest one is going to be shift operation 0, which we've picked to be the 0 operation. So basically not feed anything through the multiplexers, but just set the left-hand side to 0. So in every multiplexer, option 0, we can just tie to ground, such that when option 0 is selected, we're just producing a 0 value at the output. So that's pin 6 on one side of the multiplexers. And pin 10 on the other side of the chips. Alright, so that's option 0 all hooked up. The leftmost multiplexer doesn't deal with the data flowing into the left-hand side, but this one we'll use to pick the appropriate carries to inject into the shift and also to inject into the adder. So we'll deal with this at the end. Now it's time to actually connect a left-hand side input to these multiplexers, which then will produce a left-hand side input for the adder. And I think we want to do something similar as we did here on the right-hand side with the XOR, where we just say the leftmost 8 connections on the breadboard here, they correspond to the left-hand side input of the breadboard. And what we'll do is we'll just pick values off of these 8 most connections here and bring them over to the appropriate inputs on the multiplexers. And then this will be our spot where we can connect a DuPont cable or other logic down there to actually drive an input into the ALU. And the way this is set up, every bit in the left-hand side input into the ALU will actually connect to 3 inputs on the multiplexers because we have 3 ways how we consume the left-hand side. It's either the unshifted version, that's one of the inputs of the multiplexers. It's the left-shifted version, which is another input, and the right-shifted version, which is yet another input. So each of these input bits here need 3 connection points on the multiplexers. And as it turns out, some of them are actually in the same multiplexer. For example, the input bits 0, 2, 4, and 6 need to be connected to pins 5 and 12 of the same multiplexer. And similarly, inputs 1, 3, 5, and 7 need to be connected to pins 3 and pins 11 of the same multiplexer. So let me add these small connections across the same multiplexer first because they're very easy to do. Now, similarly, there are connections between neighboring multiplexers. For example, input bit number 1 needs to be connected to pin 3 of this multiplexer and pin 4 of this multiplexer. And similarly, input bit number 2 needs to be connected to pin 13 of this multiplexer and pin 12 of these multiplexers. So let me make these connections between neighboring multiplexers next because they're pretty easy to do as well. Alright, so that's all the neighboring connections done. And now that these things are out of the way, let's actually go take the inputs here from the left-hand side of the breadboard and bring them over to the multiplexers. And we're going to use the same order as we did with the bar graph LEDs here. Bit 0 is going to be on the right, and bit 7 is going to be all the way on the left. So let me hook this up. Pretty sweet, that gives us an 8-bit input here all the way on the left of the breadboard, which feeds the appropriate bits into the multiplexers at the right locations, and then the multiplexers produce an output. Now we're actually missing two input connections. All the way on the right-hand side here, this multiplexer which picks bit 0 for the adder input, we need to decide what bit we're shifting in when we're doing a left shift. And then all the way on the left here, the multiplexer which picks bit 7 of the number that goes into the adder, we need to pick what gets shifted in when we're doing a right shift. Both of these inputs we want to connect to the carry multiplexer and basically just use whichever carry we have picked with this multiplexer here. This will give us quite a bit of flexibility because using this multiplexer, the carry operation multiplexer, we can pick whether we want to shift in zeros, shift in ones, whether we want to shift in the existing carry flag, and then later on we might actually change one of the inputs here such that we can pick to shift in the current sign bit of the left-hand side, which would allow us to do arithmetic right shifts, which is pretty sweet. And the left-hand side multiplexer here, which deals with which carry we're going to feed into the adder and what we're going to do with the adder's output carry and what we're basically storing into the carry flags register. This one will have a connection to this carry multiplexer. So let me just bring over these carry connections to this multiplexer here, such that there's just one point where we need to hook this up to the carry operation multiplexer up here. Okay, pretty cool. So that's all the inputs of the 8 multiplexers down here connected, which are going to drive the left-hand side input of the adder. The thing that's still missing a few connections is the multiplexer all the way on the left here, which is dealing with the carries going around the ALU. Right now, the carry input of the adder of the ALU comes directly from the carry operation multiplexer, which was pretty useful because we could inject constant values or the current carry flag straight into the adder. However, when we're doing shifts, we're actually using this carry to shift in to the right or the left, depending on whether we do a left or right shift. And so when we're doing shifts, we actually don't want to use the carry that's coming out of the carry multiplexer directly for the adder, because it's just going to mess with the shift we're doing. And so this multiplexer at the bottom here is going to pick the carry input that we're feeding into the adder. Whenever we're doing a shift, we're going to feed in a 0 such that the carry doesn't mess with the values here. But when we're not doing a shift, we just want to pass through the value from the carry operation multiplexer. So let me remove this direct connection from the carry operation multiplexer to the carry input of the adder. And let me rewire this such that we take the carry input of the adder from this new multiplexer down here. And so, as we've just discussed, when we're doing a shift operation 2 and 3, we want to inject a 0 carry input into the adder. So options 2 and 3 of this multiplexer here, we just want to connect to ground, such that we're injecting a 0. All right, and if we select carry operation 0 or 1, basically feeding in a 0 or feeding in the left-hand side unchanged, we want to take the carry that's picked by the carry operation multiplexer here and just pass that through to the adder's carry input. So let me connect options 0 and 1 of this multiplexer together and then hook that up to whatever comes out of the carry operation multiplexer. All right, so that's the carry input of the adder selected appropriately. There's a similar situation with the carry flag up here and what we're presenting to the carry flag register as the next carry flag to be stored. Right now we're just taking the carry output from the adder and that's our next value that we're storing into the carry flag register. However, in a similar kind of line of reasoning, when we're doing a shift operation, just shifting things left and right, we actually want to take the bit that we're shifting out, the one that's no longer present in the left-hand side, we want to store that into the carry flag such that we can still use it. And so instead of making this a direct connection from the adder's carry output to the carry flag register, we actually want to pick carefully what we store into the carry flag register. And we're going to use this other multiplexer that we still have left over up here. It's going to pick what the next carry flag register value should be depending on what the current shift operation is. And for carry operation 3, we're doing a right shift, which means that we're shifting all the bits to the right such that the lowest bit in the input actually drops out of the number. And that's the bit we want to store into the carry flag. So when we do a right shift, option 3, we want to take the lowest bit in the input, the one that gets dropped, and forward this to the carry flag register. And similarly, when we do a left shift, the topmost bit, number 7, is the one that's dropping off of the number. And we want to take that drop bit and store it in the carry flag register. And in all the other cases, when we're injecting 0 or we're just passing the input through unchanged, we just want to take whatever the carry output of the adder is and forward this to the carry flag register. So let me take the carry output of the adder to options 0 and 1 of the multiplexer. And the input of the carry flag register here, this wire that goes currently to the adder's carry output, we now want to take from the output of this multiplexer here, which picks what we're going to store in the carry flag register. So when we pick carry operation 3, a right shift, we want to take bit number 0 and forward it to the carry flag. So let me connect input option number 3 of the multiplexer to bit 0 of the left-hand side input. And similarly, when we pick shift operation 2, we want to take bit number 7 of the input and store that into the carry flag register. So option input number 2 of the multiplexer, let me connect that up to bit number 7. Alright, so that's the other multiplexer hooked up that lets us pick carefully what we put into the flag register. And so the only thing that's left to do is to connect the outputs of the multiplexers down here to the left-hand side input of the adder. Alright, so that's all the connections made. Let me clean up a few of these wires that are currently pretty loosely connected. These can be just proper actual breadboard wires. Let me give this a quick cleanup. Alright, nice. I'm always happy to get rid of some of these loose wires. I think I'm going to leave these connections for now because this is part of the ALU that will still change in the future, but this shifter looks pretty good. I think that's all we need to do the bit shift on the left-hand side input of the ALU. Let me power this up and let's do a quick smoke test to see if the basic functionality works. Let me set the clock enabled to low. And let me toggle the clock such that we clock in this 0 bit as the carry flag. Let me set the carry operation to 0 and the shift operation to 0. Let me wire up a pattern to the left-hand side. That is going to make it easy for us to see if we're doing the shifts properly. And I'm starting to see some instability here in the power connections, so let me go check out what's going on here. I think I have a connection wrong here. Change that. There we go, that looks a lot better. No instability of power, just a bug on the breadboard. This looks pretty good already. We're selecting shift operation 0, which is the 0 operation, and we're ignoring what's on the left-hand side input of the ALU. We're just feeding a constant 0 into the adder. And that seems to be working. I've hooked up a non-zero pattern on the left-hand side, but regardless of that, you can see that the left-hand side input of the adder up here is a 0. So the multiplexers seem to do the right thing, which is pretty sweet. Let me select shift operation 1, which is going to be the pass-through operation, where we're just passing through whatever's on the left-hand side to the left-hand side input of the adder. And indeed, that's working. That's the pattern I've connected to the left-hand side input of the ALU. Let me quickly toggle the clock here at the carry flag register, such that we have a 0 in there. There seems to be some unreliability in the clock here at the carry flag register. Let's see if we can figure out what's going on there as we go along. I've also just noticed that this connection here, this used to be the right-hand side invert signal, isn't connected yet. So let me bring that back down here to the subtraction control signal of the right-hand side XOR gates. Whenever this is 1, we want to invert the right-hand side. That's shift operation 1 working. We're passing through the left-hand side unchanged. Let's try to produce an overflow in the adder here such that we can check whether the carry output of the adder gets properly presented to the carry flag register. Let me just set the topmost bit on the right-hand side. That should be enough. Just realized that I forgot to hook these power connections back up of the XOR inversion chips. Let me rectify that quickly. All right, that's back to being operational. And as you can see, the topmost bits on the left and the right-hand side of the adder input are set. So that causes the adder to overflow, produces a carry output. And this carry output goes through the multiplexer down here and gets presented at the carry flag register up here. Let me set that back to 0. Let's try a left shift. That is shift operation number 2. And that looks pretty promising. As you can see, the pattern shifted left by 1 position, and the one that got shifted out by the number is now presented at the carry flag register as the next carry flag to be stored. So basically we're shifting the number left, and whatever drops out of the number we're storing in the carry flag register, which is exactly the behavior we're looking for. And if I toggle that leftmost bit, the one that gets shifted out, we should see the carry flag input here toggle accordingly. And that's exactly what happens. Let's try a right shift operation. That's carry operation number 3. And that also seems to work. As you can see, this is now the input pattern shifted right by 1 position. And the bit that got shifted out at the far right here is now presented at the carry flag register. And so if I toggle that far right bit, you should actually see the carry flag register input toggle accordingly. And there you go, that seems to be working. We're still having some weird instability here with the clock signal. Let me look into that a bit more. And we seem to be back to operational. It looks like this clock wire here isn't always making proper contact. That's the downside of doing everything on breadboards. The connections are sometimes quite a bit unreliable. But we're just using this for debugging and testing to build it up. And as soon as this is all done, we'll move it to a proper PCB, make it quite a bit more compact, and then we'll have a pretty reliable system that is going to be more fun to work with. So that's all the shift operations working. We had operation 0, which produced a 0. We had operation 1, which just produced the input unchanged. We had operation 2, which produced a left shift, and we have operation 3, which produced a right shift. And we saw the carry input to the carry register be set to the appropriate value. Let's also test if we're properly shifting in the bit produced by the carry op multiplexer here. So when we're doing a left shift, whether we shift in the right least significant bit, and if we're doing a right shift, that we're shifting in the appropriate leftmost bit. Let me quickly set the carry flag register to 1 by clocking it, because we're currently presenting a 1 at its input, so that's pretty straightforward. We're currently doing a right shift, so the carry operation multiplexer is dictating what the topmost bit is going to be, the bit that's being shifted in. Right now the carry operation is set to 0, which produces a constant 0 value as the carry. Let me change that to carry operation 1, which is going to produce a constant 1 as the carry. So we should see a 1 being shifted into the number here at the topmost bit. And that's exactly what happens. The carry operation multiplexer here produces a 1, and that 1 gets shifted into the top of the number here. But as you can see, this currently has the side effect of also enabling the right-hand side inversion, because we have this hardwired connection here to the inverter. So the adder is actually doing some stuff. We'll get rid of this connection later on when we do proper decoding of the ALU operation. But for now, let me just pick carry operation 2, which is not going to do the right-hand side inversion, and it's just going to forward whatever's in the carry flag to its output. So essentially what we should be able to see is the current state of the carry flag register, the 1, being shifted in at the top. And there you go, much better. So we're using the carry flag register value, and we're shifting it in at the top when we're doing a right shift. Let's change the shift operation to a 2, which is a left shift, which should see us shift in the carry flag at the bottom end of the number. And that's exactly what happens. The whole pattern shifted to the left, and we're shifting in the current state of the carry flag, the 1, at the bottom end of the number. And if I change the carry operation to a 0, the carry operation multiplexer here is going to produce a 0 at its output, which means that at the bottom end of the number here, we're actually going to shift in a constant 0, which is exactly what happens. This looks very promising, so looks like this whole wiring mess that we produced here with all the multiplexers does the right thing. We can shift input values to the left and to the right. We're shifting in the appropriate carry bit that we're selecting with the carry operation multiplexer here. We can also just do a regular pass-through, in which case nothing happens, and we can pass in a 0 even, where the left-hand side is just set to a constant 0. And if we're doing a shift, we're presenting the shifted out bit to the carry flag up here, such that we actually have a place to store it for future use. And if we're not doing a shift, if we're passing the value through or we're injecting a 0, we're just using the carry output of the adder and present that to the carry flags register. So that should allow us to do the regular add and add with carry that we had before, but now we also have the option to do the left and right shifts with the appropriate interaction with the carry flags. In the next episode, we're going to integrate the ALU back into the CPU. There are a few new control lines that we need to wire up, which we can then use in our new shift instructions. And it would be great to write a small test program that uses the shifts to do some useful work and do some interesting things. Thanks a lot for watching, like and subscribe if you want to see more of this, and see you next time.